Have you ever wondered how a calculator can add numbers? Or how you're able to stream hundreds of thousands of hours of video straight to your phone? What about how computers are so good at playing chess? Well, when I was in sixth grade, I had these same questions, and I began to teach myself computer architecture to finally unlock those secrets. Pretty soon, I designed my first computer, and the rest is history. Hi, my name is Benjamin Saunders, a senior with the MST Magnet program, and welcome to Project MANIAC. The heart of any computer is the central processing unit, the CPU. This component is single-handedly responsible for interpreting and running every program on the system, and carrying out every calculation required by those programs. Since the advent of the modern CPU in the 1950s, computers have quickly become smaller, increasingly powerful and feature-rich, and more power efficient. What used to take up a large room is now easily able to fit in your pocket. In order to retrace these astonishing developments myself, I embarked on a year-long project designing my own CPU. Among various technical goals and benchmarks I hope to achieve, the MANIAC architecture was to build on my prior knowledge by introducing concepts such as virtual memory and paging that helped isolate programs from each other, affording the user increased security while simplifying program development in general. Additionally, MANIAC was to add support for a kernel, the central part of an operating system that manages programs and creates a stable and safe environment for them to run. And finally, MANIAC had to support interrupts. An interrupt is any asynchronous event the CPU cannot predict. This could be typing on your keyboard, or moving your mouse across the screen, or plugging in a USB stick, or they could even come from within the CPU itself, such as when a program tries to do something it really shouldn't. These events need to have special hardware so they can be handled immediately. In order to accomplish the goals I set out for myself, I started with a very basic framework that I could build on over time. This was MANIAC version 1. By the start of this project, I had built up that initial design through version 3.2, which, among other features, demonstrated MANIAC's capability to service interrupt events by implementing a Programmable Interrupt Controller, or PIC. Little did I know, I was just getting started. Slowly, I built the CPU to version 4 and then version 4.1, making huge strides in memory control techniques and redefining what many parts of the computer meant to simplify the instruction set. More than 184 sources later, I finally had everything I needed to realize all my goals in version 5, the most complex CPU I have ever designed. However, just because I had the hardware down did not mean the CPU could interpret code or perform any useful actions. No matter how close to the metal you get, every computer requires a set of standardized instructions the CPU can understand. This is called the instruction set architecture, or ISA. One of the major challenges in designing a computer is the constant balance the engineer must keep between the instruction set and the CPU. If the CPU advances, so must the instruction set it runs. Each is dependent on one another. While I designed MANIAC version 4 and 4.1, I had to develop version 2 of the instruction set in parallel. That's shown here. While I designed MANIAC version 5, I had to constantly keep in mind the development of instruction set version 3. In practice, it is very difficult to keep everything in balance and in the front of your mind at the same time. Unfortunately, these weren't my only challenges. At such a low level of design, the resources I needed were often scattered between a dozen or more articles, obscure university slideshows, or patent filings. In some instances, the information I was looking for simply didn't exist on the internet. Fortunately, I had an expert at my disposal, my mentor, Giovanni Viscardi, a professional computer engineer and business owner in Richmond, Virginia. He's working as well to develop his own state-of-the-art CPUs. Geo has always been free to help me answer those burning questions or give me suggestions when I've gotten lost. Always encouraging me to explore my own solutions even when they're non-standard or suboptimal, I could ask for no better mentor to guide me through this project. Overall, I have learned so much more than I thought possible. Beyond just the technical aspects, it has taught me to never stop being ambitious because although I set myself up for a much bigger project than I anticipated, I gained valuable skills, made valuable connections, and achieved far more than I could have hoped for. After accomplishing all my goals, I am still plagued by new and unanswered questions and hope to move to yet more complex architectures soon. But before I do so, I have plans, with help of my mentor, to construct a real working version of the MANIAC architecture as a visual testament to my work in computing. Thank you for watching.